Hello and welcome to our next video in our series on partial fraction decompositions. In this video, we are going to address the question as to whether or not expanding repeated factors is necessary. Now, in this video, we are going to examine a few examples with repeated linear factors to show that if you do not expand them properly, then you may end up with a issue as far as determining the decomposition. So our objective for this video is to demonstrate why repeated factors must be expanding using all the lower powers. Again, we'll be using linear factors here. The same idea would exist with quadratic factors. It just gets a little bit more complicated with the arithmetic, but I believe the point will be made with repeated linear factors. So our first example has x squared plus 6x minus 7 divided by the quantity x cubed times the quantity x minus 2. Now, if we just rewrite our partial fractions template as a divided by x cubed plus b divided by x minus 2, which is already kind of erroneous, but if we try to just do it this way, then we will end up with a system of equations that has 0 equal to b, which happens to correspond to the coefficients of x cubed, 1 equals 0, that would be the equation associated with the coefficients of x squared, 6 equals a, this is the coefficients associated with the variable x, and negative 7 is equal to negative 2a, which corresponds to the constant terms in our system. Now we notice that we have several problems here. One, we have, according to our system, it's inconsistent because one of our equations was 1 equals 0. This is a completely false equation. We also have b equal to 0, which suggests that the term that b divided by x minus 2 is not needed in the expansion. But x minus 2 is a distinct linear factor for the denominator, so it is needed in the expansion. So b equals 0 gives us a contradiction. Here we also have that the value of a, the numerator over x cubed, actually equals two different values. We have a equals 6 and a equals 7/2, which is not possible. And all of this is resulting from the fact that we did not expand our x cubed factor properly for the denominator. We didn't write out all of the lower powers on x to get that repeated linear factor. So the expansion was not done properly. If you use systems to solve these things, the system of equations approach points out a lot of these issues. This particular decomposition is going to violate existence and uniqueness, which we already know exists for partial fractions, and therefore the decomposition is incorrect. And the problems all start with how we try to write out our template, because we didn't pay attention to the rule on how to expand repeated factors. Now, if we do this correctly, we are going to have x cubed expanded as x squared, and x cubed. And then we'll have x minus 2 as its own denominator. So when I have a over x plus b over x squared plus c over x cubed plus d over x minus 2, this is the correct way to expand this repeated linear factor situation. When I combine my template and match up the numerators and the denominators, match up the coefficients for the numerators, we end up with a system of 4 equations and 4 unknowns, where we have a plus d is equal to 0. That happens to correspond to the coefficients of x cubed being matched. The coefficients of x squared match up as negative 2a plus b is equal to 1. The coefficients of x match up as negative 2b plus c equals 6. And the constants match up to form the equation negative 7 equals negative 2c. So this system, even though it's a 4x4 system, may be solved by back substitution. The last equation gave us c equal to 7/2. It's continuing the back substitution approach, we end up with the b numerator being negative 5/4, the a numerator being negative 9/8, and the d numerator being 9/8. So our decomposition of x squared plus 6x minus 7 divided by x cubed times the quantity x minus 2 will be rewritten in its partial fraction decomposition as negative 9/8, all of that divided by x, plus negative 5/4 divided by x squared, plus 7/2 divided by x cubed, plus 9/8 divided by x minus 2. Now here we have another one that has repeated factors. So here we have x plus 4 divided by x squared times the quantity x minus 1. If we expand this out properly, we have a over x plus b over x squared plus c over x minus 1. Combining these fractions, and we have x plus 4 over x squared times the quantity x minus 1. And this is going to be equal to ax squared times x minus 1 plus bx times x minus 1 plus cx cubed. All of that's divided by x cubed times x minus 1. Now, if we match up the numerators, we get x plus 4 is equal to ax cubed minus ax squared plus bx squared minus bx plus cx cubed. Matching up our coefficients, we have a plus c is equal to 0. That's the coefficients of x cubes matched up. For x squared, we have 0 is equal to a plus b. We have 1 is equal to negative b. That happens to be the coefficients of x. And finally, we have 4 equals 0, which happens to match up the constants. So here we've come across another issue. The issue that arises is that when we combined without using the least common denominator, we did not reduce the expression before forming the system. It essentially shifted the coefficients up 1 power on x and therefore caused a mismatch in the coefficients. If you noticed in the second step, we could have removed the extra factor of x, which would have kept everything in balance. If you also notice, the denominators did not match in that second step, which is the result of not reducing the fraction before forming the system. So this example demonstrates that if you are not finding least common denominators before you do the decomposition, your coefficients could be off. And again, the systems of equations approach is going to bring this to light by showing you some kind of inconsistent system. So when we do this properly, okay, we have the same breakdown, we have the same template, but on the second to last step of the slide here, we were able to factor out an x from the numerator. That x in the numerator cancels with the x cubed in the denominator, and now we have x squared times the quantity x minus 1 on both the left and the right side of my decomposition. And that gives us an indication that now we're ready to match up the numerator's coefficients, now that the denominators match perfectly. So when we match up the coefficients, our system is now 3 by 3 instead of 4 by 4. And we have a plus c is equal to 0. That's the coefficients of x squared equation. The coefficients of x equation has negative a plus b equal to 1. And the constants equation has 4 equal to negative b. This is a 3 by 3 system, but we can reduce it to a 2 by 2 system since b is already equal to negative 4. With that, we can determine the value of a, which is negative 5, and the value of c, which is positive 5. Therefore, the decomposition of x plus 4 divided by x squared times the quantity x minus 1 is equal to negative 5 over x plus negative 4 over x squared plus 5 over x minus 1. So please be careful that when you are recombining your template, that you use the form of that template that it has the denominators match with the original. Reduce them down so that the denominators match. Once the denominators match, then you're ready to match up the coefficients in the numerator according to the powers on the variable. So notice that partial fraction decomposition does root out any errors in the process, or if there's some algebraic oversight, such as not reducing the fractions down before you form the system. This also demonstrates how important it is when performing the decomposition with repeated factors. The expansion covers all the lower powers of the factors as well as the current power. This is not done properly. The decomposition template, when you go to reform the system, is going to tell you that something is wrong. Either there'll be an inconsistent system, there'll be answers that don't make sense, or something like that. So the system's approach to solving partial fractions, when you do it by hand, is, in my opinion, the most effective, because any mistakes that are made are going to come to light when you try to form the system. Thank you for your time and attention.